Good morning. Today we have got the discussion of physics paper 27. First question. Which of the following Bohr model is not valid? Bohr model is only applicable to simple structure of atoms like single electron structure. It is directly applicable to only hydrogen atom and also can be extended to hydrogenic atoms like singly ionized helium, doubly ionized lithium, triply ionized beryllium, so and so. Anyway, the atom should have only one electron in the orbits. So here the answer is option 3. Singly ionized neon atom, it cannot be applied to Bohr model. Okay, but deuteron atom, that means deuteron has got one proton only, so one electron only it carries in the orbit, so it can be. Singly ionized helium also possible. Hydrogen atom also possible because has only one electron in the orbits. So answer is third option is the right choice. Second one. Next, the total energy of electron in an atom minus 3.4. That can be the second orbit of hydrogen atom, because as per Bohr model, first orbit of hydrogen atom has got minus 13.6, second orbit minus 3.4, third orbit minus 1.5, fourth orbit minus 0.85, like that. Here, minus 3.4 is the total energy. Total energy is negative of the kinetic energy, or kinetic energy is negative of total energy. Kinetic energy will be plus 3.4 and potential energy will be 2 times total energy. Potential energy will be 2 times total energy. Total energy given minus 3.4. So total energy minus 3.4, potential energy 2 times, that is minus 6.8. So the correct option is second option. Third one, ratio of kinetic energy to that of total energy of electron in Bohr orbit of hydrogen atom. Here to that of total energy, you please add total energy. Add total to total energy. Total energy, the ratio is 1:-1 because kinetic energy is numerically equal to total energy, or kinetic energy is negative of total energy. So the ratio should be 1:-1. Next one, the ratio of wavelength of last line of Balmer series and last line of Lyman series. You can see here. Energy level diagram of hydrogen atom. First orbit n=1, second orbit n=2, then now going on up to infinity. The last line of Balmer series, all it ends at 2, and last line will be the longest line, the energized transition of Balmer series, that is infinity to 2. Last line of Balmer series is infinity to 2. First line of Balmer series is 3 to 2. Now last line of Lyman series is infinity to 1. First line of Lyman series is 2 to 1. Last line of Lyman series is infinity to 1. That is the energized transition of Lyman series. The wavelength corresponding to this one is 1 by r. Wavelength corresponding to this one is 4 by r, where r is Rydberg constant. 1 by r, easy to remember, all perfect squares. 1 by r, 4 by r, and the next one, transition from infinity to 3 will be 9 by r, transition from infinity to 4 will be 16 by r, next will be 25 by r. The last transitions of each of the spectral series you can easily find out. Wavelength can be found out by using this law. 1 by r, 4 by r, 9 by r, 16 by r, 25 by r. Easy to remember. Now, what is the ratio? Ratio will be 4. So third option is the right choice. Fifth one. An electron in hydrogen atom jumps from third orbit to second orbit. Third to second. Let me draw it. Then only you will be clear with this. Third to second. n=1, 2, 3. Third to second. photon of wavelength lambda is emitted. So we can use the connection or relation 1 by lambda is equal to R into 1 by the state to which transition occurs, 2. So 2 square minus 1 by the state from which transition occurs, that is 3 square. Okay. On solving, you get what? 1 by lambda equal to R into 1 by 4 minus 1 by 9. That implies R multiplied by, here you get 36, here you get 5. So 1 by lambda equal to R into 5 by 36. Similarly, you follow the same steps. 1 by lambda dash is equal to, from where to where? That is from 4th to 3rd. That is 1 by 3 square minus 1 by 4 square. Okay. If you follow the same procedure, you will get R multiplied by, you will get 7 here, you will get 144 here. Okay, easy to remember. When you jump from 3 to 2, 3 plus 2, you write 5 here. 3 into 2 is 6, 6 square is 36, you write here. Okay, no need for going to this. If the transitions are neighboring, you can use a shortcut there if the transitions are neighboring. Okay, that 3 to 2, 3 plus 2, 5, 3 into 2, 6, 6 square 36. Next one, another transition was 4 to 3, 4 to 3, 4 plus 3, 7, 4 into 3, 12, 12 square 144. Okay, you take the ratio, you will get lambda dash as 20 by 7 lambda. You divide these two, you will get the answer option 1. Sixth one, spectrum of hydrogen, the ratio of longest wavelength in Lyman series. Longest wavelength in Lyman series mean what? Infinity, n equal to 1, 2, 3, 4 up to infinity. Longest wavelength means shortest energy. So shortest line. This will be smallest energy transition. 2 to 1. That is longest wavelength. So that is lambda maximum for Lyman. Now, to longest wavelength in Balmer. Longest wavelength in Balmer will be, for Balmer all transitions are up to 2. So shortest line will be 3 to 2. That is corresponding to lambda max in Balmer. Now Lyman, you know this ratio. What is this wavelength lambda maximum? 2 plus 1 is 3. 2 into 1 is 2. 2 square is 4. So you get 4 by 3 R. Here you do the same. 3 plus 2 is 5. 5 divided by 3 into 2 is 6. 6 square is 36. So 5 by 36 R. So here 4 by 3 R. Sorry, here 36 by 5. Made a mistake. 36 by 5. 3 into 2, 6. 6 square 36. Here first you take the product and square. 1 plus 2, 3 is in the denominator. So 3 plus 2 is 5. 5 R. Okay. Now what is the ratio? Ratio first Lyman. So 4 by 3 R multiplied by 5 R divided by 36. 36 and 4 cancels. You get 9 here. 5 divided by 27. So the right option is option 1. Seventh one. Ratio of areas within the electron orbits for the first excited state to ground state for hydrogen atom. First excited state means n is equal to 2. Okay. And ground state means n equal to 1. We know radius of nth orbit. We have used the formula Rn is equal to n square h square epsilon 0 divided by pi m z e square, where R proportional to n square. Okay, area, orbit is circular, so area proportional to pi r square. Area pi r square, so area r square. Then R already n square, so area proportional to n raised to 4. N raised to 4 fourth power. So it should be 16:1. 18. Bohr model of hydrogen atom, ratio between period of revolution of electron in n equal to 1 and that of 2. Time period. Time period is proportional to cube of quantum number. So T proportional to n cube. That's why the correct answer is 1 by 2 cube. That is 1 is to 8. Ninth one. There are discrete energy levels demonstrated for the first time through Frank-Hertz experiment. Knowledge level question. 10th one. R is Rydberg constant, energy, total energy. The shortcut formula to express total energy, when you express in joule, minus Z square RCH by N square. For hydrogen atom, Z is equal to 1, and also in first orbit, N is equal to 1, so you get minus RCH is the right answer box. 11th one. Electron jumps from fourth orbit to second orbit of hydrogen atom. Rydberg constant is given. What is the frequency of the emitted radiation? We can use the Balmer formula, which is 1 by lambda equal to R into 1 by fourth to second. The state to which transition occurs is 2. So take 2 square minus 1 by 4 square. You do these calculations and write R into 1 by 4 minus 1 by 60. That is, you will get 3 by 60. Okay. Now, you see, I am multiplying by C on both sides. Multiply by C on both sides, where C is speed of light. Where C by lambda is frequency F. Frequency is C by lambda, so you use RC. The value of R taken to be 10 power 7. C, you know, 3 into 10 power 8 into 3 divided by 16. So 7 plus 8 is 15. So 9 by 16 into 10 power 15. So correct option is C. 12th one. Hydrogen atom emits a photon of wavelength 4860 angstrom. The change in kinetic energy of electron in the state. What is the wavelength emitted? So we find out the corresponding energy. The corresponding energy E is equal to HC divided by lambda. Okay. HC, all these substitutions are made lambda. Okay. For that we have got a shortcut. If you use this formula, you intend to use this formula, you have got a shortcut to get the answer, but you get the answer in electron volt. Okay. E is equal to the formula 12400 divided by 4860. Okay, when you do this, you get 2.56 electron volt approximately. So we say the wavelength released corresponding to an energy released, which is 2.56 electron volt. The released energy will be the change in energy of the hydrogen atom. So the correct answer is option B. 13th one. Rydberg constant is given. Wavelength of first line of Lyman series in hydrogen spectrum is equal to first line. First line in the Lyman series is from 2 to 1. 2 to 1, what is the corresponding wavelength? Lambda is equal to 1 into 2, 2 square is 4, 1 plus 2 is 3. Now, this is the shortcut that we use now thrice. Lambda equal to 4 by 3 R. 4 by 3 you can write 1.3 something. Okay. Approximation only needed. Divided by R. R is 1.097 into 10 power 7. This can be very close to, slightly greater than 1. That's why it will be slightly less than 1.3. Let it be 1.2. Okay. Into 10 power minus 7 meter. To convert into angstrom, that is in meter. You convert into angstrom, you multiply it by 10 power 10. So you get very close to 1.2 into 10 power 3. So very close to 1200 angstrom. This is in angstrom. I converted into angstrom. So the answer should be in angstrom. So A is not the right answer, but C. Don't forget to watch the units in each of these options in similar questions. 14. Energy levels ABC of certain atom corresponding to increasing the values of energy, that is EA, EB and EC. EA less, EB less, EC is given. Lambda 1, lambda 2, lambda 3 are wavelengths of radiations corresponding to the transitions C to B, B to A and C to A of the following relations, the one which is correct. We use energy conservation here. You see, these are those levels mentioned, A, B, C. Okay, correspond to increasing values of energy. That is, A is least, C is greater. So we know total energy increases as you move away from the ground state. Ground state energy is minimum, total energy minimum, potential energy minimum, but kinetic energy maximum. As you move away from the ground state to higher states, what happens? Total energy increases, potential energy increases, at the same time kinetic energy decreases. Okay, so as you move away from the ground state to upper orbits, total energy and potential energy both increases and kinetic energy decreases. So here C, B and A. Okay, the transitions wavelength lambda 1, C to B, lambda 1 C to B, lambda 2 B to A, and lambda 3 C to A directly, that is lambda 3. We know for applying energy conservation, the total energy between C and A may be E3. Let it be E3, the transition delta E3. That is equal to, in the case of third to first one, that is C to A, that is the energized transition. That energy difference will be equal to sum of energy difference of E1 and E2. This energy difference is equal to energy difference between these two plus energy difference between these two levels. So E3 equal to E1 plus E2. But we know energy, transited energy, that is the released energy, delta E, that is E1. Delta E is E1 between that corresponding levels. So delta E transited energy or released energy is equal to hc by lambda, that appears in the form of a photon. So hc by lambda. So that hc by lambda appears in each of the terms of, I'm not writing hc, gets cancelled. So this can be written 1 by lambda 1, hc by lambda 1, hc gets cancelled in each side. So this is lambda 2, here you get lambda 3. So this is the right answer. So lambda 3 equal to lambda 1 lambda 2 by lambda 1 plus lambda 2 is a good question. 15th one. Consider spectral line resulting from transition 2 to 1 in the atoms below. Shortest wavelength from Balmer formula 1 by lambda proportional to z square. 1 by lambda equal to z square r into 1 by n final square minus 1 by n initial square. The formula we have learned. Here lambda and z square varies inverse relationship. That's why shortest wavelength, to have lambda minimum, z should be greatest. And among the following, z is greatest for lithium. So answer is dog. But Bohr model is only applicable to single electron structure. That's why doubly ionized lithium is written. 16th one. Velocity of electron in ground state is v. Ground state radius is r. Jumps to another orbit where speed is 1/3. Speed has become 1/3. The formula for velocity of electron in nth orbit of hydrogen atom is Zc divided by 137n. This shortcut can be used. Okay. Otherwise, we have the direct formula. You can also use this Z square by 2 epsilon 0 nh. Z square by 2 epsilon 0 nh is also used for finding the velocity. Anyway, velocity in nth orbit is found to be proportional to 1 by n. Okay, this is a shortcut. This also can be used as a shortcut. So velocity proportional 1/nth. Velocity 1/3, that means n is equal to 3. So the transition has taken from ground state to n is equal to 3. Okay, but we know the radius is proportional to n square. N square. So 3 square 9. So answer is 9r. 17. Energy of electron in excited state of hydrogen atom is minus 3.4. Minus 3.4 for hydrogen atom, it must be in the second orbit. Bohr's quantization condition. We know angular momentum in nth orbit is equal to n times h by 2 pi. Okay, so here n is equal to 2, it's clear, because total energy is minus 3.4 electron volt. So second orbit, what is the angular momentum? You get 2 times h by 2 pi. 2h by 2 pi. Okay, we know the value of h by 2 pi is very close to 1.05 into 10 power minus 34. the value of h by 2 pi you need to by heart. That is very close to 1.05 multiplied by 10 power minus 34. Don't forget to by heart the value of h by 2 pi. Okay, need not calculate that time. You try to calculate, you will get very close to this value. But here twice. That's why answer is option 2.1 into 10 power minus 34. 18. Transition of electron in hydrogen atom from third to first orbit is lambda. Repeated. Let me do it. 1 by lambda equal to or proportional to 1 by third to first, 1 by 1 square minus 1 by 3 square. That is 1 by lambda proportional to 1 minus 1 by 9. That is 8 by 9. Okay, it's 1 minus 1 by 9. So that's 8 by 9. Second case, 1 by lambda dash proportional to where to where? Fourth to second. Fourth to second. So 1 by 2 square minus 1 by 4 square. That is 1 by lambda dash proportional to here comes 4, here comes 16. So it becomes 3 divided by 16. So you get 3 by 16 here. Okay, that is. We have to know what is lambda dash. For that, you take the ratio, you get lambda dash as 128 divided by 27 lambda. You try to take the ratio. The correct answer is option D, 19. Potential energy of electron in hydrogen atom is very clear, double the kinetic energy in magnitude. Okay, potential energy is twice kinetic energy. Total energy is numerically equal to kinetic energy. Like that we have learned the triangular relationship between kinetic energy, potential energy as well as total energy. Speed of electron in first orbit of hydrogen atom. I have used earlier a shortcut where it is Zc by 137 and you can use this shortcut. Here first orbit for hydrogen atom Z1, first orbit n equal to 1. So that is C by 137. So the right choice is option C, 21. Rydberg constant is, you have to by heart this, m e raised to 4 by 8 epsilon 0 square Ch cube. By heart it. M e raised to 4 by 8 epsilon 0 square Ch cube is the Rydberg constant. Its value is 1.097 into 10 power 7 per meter. Unit of Rydberg constant is per meter. Don't forget. L inverse. Line spectrum is obtained when substance is in the atomic state and band spectrum in the molecular state. Rutherford scattering experiment with gold foil. 232 scintillations per minute are observed at an angle 30 degree. The number of scintillations at an angle 120 degree is. The number of alpha particles scattered through an angle theta is found to be proportional to 1 by sine raised to 4 theta by 2. This is the relation to be used. That is, we have to know the angle 120. So number 120 divided by number 30, that's equal to. Ratio when you take sine raised to 4 theta by 2. Here 120. So as inverse, you have to use 120 by 2 here, that is 60. Okay, sine raised to 460, and here you have to use sine raised to 415. So sine 30 is 0.5. So sine 15 is nearly half that. So 0.25. 0.25 I can write 1 by 4. So I will write 1 by 4 all raised to 4 divided by sine 60 is root 3 by 2. So sine raised to 4 60, that is root 3 by 2 all raised to 4. You compute this, you get an approximate value of given in option A, 24th one. Which one of the following statements regarding Rutherford's scattering experiment is not correct? It's a very good question. First option. Higher the energy of incident particle, smaller will be the number of particles deflected through a given angle. When you observe the number of particles deflect through a given angle, when you increase the kinetic energy of the incident alpha particle or any other incident particle, we change the nature of the particle, smaller will be the number of particles deflected through the given angle. That is correct. We have to know which statement is incorrect. That's important. First option is statement is correct. That's why that's not the correct answer. So this is not the answer because that statement is true. Option B. an increase in the thickness of the film. When you repeat the alpha particle experiment, by increasing the thickness of the film, we find that as the thickness is increasing, for small thickness only it is true, not very large thickness. For small thicknesses, when the thickness is increasing, the number of target nuclei to be hit would increase. That's why more number of target gold nucleus, if you use gold target, gold nucleus number would be very large when you increase the thickness. Then the scattering also would increase. But it is given it decreases. That's why that is the incorrect statement and the right answer. So here it is written decreases, actually that is increases. Okay, it's based on, purely based on NCERT textbook. Okay, you can also go through the rest of the options. Very important. 25th one. According to Bohr model of atom, kinetic energy of electron in atom decreases with the increasing radius. I said earlier also, speed decreases when you go away from the ground state. When you go from ground state to higher orbits, speed decreases, kinetic energy decreases, potential energy and total energy but increases. But in each of that orbits, each of that energies will be remaining constant because orbit is circular. 26th one. Bohr model quantization condition is not taken into consideration. If you do not consider the Bohr model and quantization of energy, that means the energy as per Bohr model, only the atom releases energy when it goes a transition from higher level to lower level. If you do not consider that, according to the classical electrodynamics, that means use the classical electrodynamics theories apply as Rutherford has applied to this atomic model. What happens to that electron? Classically, we know that electron, as per electrodynamical theories, electron when accelerating electron will radiate energy continuously. Accelerating charges radiates energy in the form of electromagnetic radiations and photons. And that electron, on releasing the energy continuously, spirals into the nucleus, falls into the nucleus in spiral path, not in helical path. It is in spiral path. Okay. Spiral path is two-dimensional, helical path but three-dimensional. It is only 2D path. So the correct answer is option B, 27th one. Rutherford's alpha scattering experiment. Alpha particle when collides with the gold nucleus, there is a maximum transfer of energy. It is possible only when the angle of scattering is 180 degree. For a head-on collision between alpha particle and gold nucleus only it is possible. For head-on collision, the angle of scattering is 180 degree. Okay, that collision is called head-on collision, where impact parameter is 0. That means the centers of masses of alpha particle and gold nucleus will be along the same line. Okay, but the gold nucleus is nearly 50 times massive than the alpha particle. Gold nucleus remains stationary. Alpha particle recoils. Okay, that is called reverse scattering. Okay, that is answer is in box. 28. Radius of first orbit of hydrogen atom is given. That is called Bohr radius, 0.528 angstrom. Radius of third orbit, we know radius proportional to n square. For third orbit, it will be 3 square, 9 times the radius of first orbit. 9 times 0.528. So correct answer is option A, 4.7 angstrom. 29th one. When hydrogen is bombarded by 10.2 electron volt and 12.1 electron volt, as in Frankfurt's experiment, which is believed to be the first experiment which proved the discrete energy levels of an atom, which highly supported the Bohr model. Emission of 3 spectral lines were observed. Wavelength corresponding to 10.2 electron volt. The wavelength corresponding to the 10.2 electron volt can be found by using that shortcut. 12,400 divided by 12.2 when you do the corresponding wavelength in angstrom, and you get 1213 angstrom. So the correct answer is option A. 30 and the last one. Color of second line of Balmer series is. Students, you try to by heart these colors at least. Blue color, the wavelength ranges between 450 nanometer to 495, and violet is between 380 up to 450. From 450 to 495 only blue. It is given that the color of second line of Balmer series. What is actually second line of Balmer series? Second line of Balmer series is transition from first line is from 3 to 2. So second line is from 4 to 2. 4 to 2 we have done earlier. That is 3 by 16R. 3 by 16 or 1 by lambda we have learned. Okay, on finding out, you will get that is very close to 489 nanometer. Okay, second line of Balmer series, when you find the wavelength by using the Rydberg formula or Balmer's empirical formula, you get 489 nanometer. 489 nanometer lies between 450 and 495. So the correct answer is blue. Okay, so this may be a possible question. You try to by heart this. The students, only those who know these results by heart, will be able to answer this. Okay, then we have finished paper 27 physics part, 30 questions. Thank you.